Hello, everyone, and welcome to the latest seminar in the Smart Mobility Connection series. My name is Lisa K. Schweier, and I am the Program Manager for Mobility21 University Transportation Center and Traffic 21 Institute. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the UTC as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note, today's session is being recorded. All participants' microphones are muted. So in order to ask a question, please send Joy Mann, who is our host, a message through the chat box. Now, I would like to introduce today's speaker, Christoph Mertz. In 1998, Christoph Mertz received his PhD in physics from Arizona State University. After continuing his nuclear physics research for another year, he joined CMU Robotics Institute as research staff. There, he developed surround sensing and object detection systems for intelligent vehicles and search and rescue robots. He has also been working on a system that is based on vehicle-mounted smartphones and can determine road conditions as well as inventory and assess road infrastructure. This technology was spun out of CMU in 2016 as Dr. Mertz became co-founder and chief scientist of the startup Robotics while remaining principal project scientist at CMU. His current research focus is on how edge computing can be used to update HD maps, monitor infrastructure, and count traffic on a scale as large as a whole city. Please help me welcome him as he tells us about his University Transportation Center project, Bus on the Edge, continuous monitoring of traffic and infrastructure. Christoph?
Thank you. Thank you for the nice introduction. You actually just mentioned all the things I did in the last couple of years. So the research which you're hearing about has actually a long tradition. It's coming out of self-driving car research. I just want to mention one vehicle here. This is this blue truck. So that was many years ago, it was 86. This needed to be this is one of the first self-driving cars, which had all the computing on board, but it had to be a truck. And the computation which was on the truck is less than what's now today on a smartphone. So that's how far we got. And that's also going to be a little bit relevant for what I'm going to talk about. Just a few things. So 35 years of self-driving car research. For 10 years, I've now been working on infrastructure monitoring research. As Lisa K mentioned, 99, I joined the Robotics Institute. In 2009 is when it started with the infrastructure monitoring research on my side. And there was a fund, an exploratory funding from Traffic 21. So that's, and this UTC, which were, which organizing these talks, that's just came out of this Traffic 21. So it took me 5 years to actually prove that I can do what I wanted to do. And what I wanted to do is the algorithms, the technology, which were on where you needed to use a whole car, now use a smartphone to do that. So, and the idea which I came up is you take that smartphone, which has a camera on it, has IMU on it, has the GPS on it, like all the sensor, all the computation which was in these autonomous cars from way back. collect data and then analyze it. And when I started the research, it wasn't clear that it's possible to look at things, for example, potholes and cracks in the car. And so after 5 years, I finally, a student from me got his master's thesis from that. He showed that it's possible to analyze those images and find cracks in the road. And then 2 years later is then when we were able to spin off that technology and started the company Roadbotics. I'm going to talk a little bit about it. That's sort of our first generation of stuff which is actually working, is out in the world. And now, since about 2018, we're doing this edge computing, which I will focus my talk on. So the first generation of what we did is and which then ended up in the company Roadbotics, is road surface monitoring. And as I started to allude to, so you have a smartphone, you put it in a car, in the windshield, so it just looks out, takes pictures of the road, or takes a video of the road. After the data is collected, the data is uploaded into a computer, into the cloud, where our core AI system is working, looking at those images, finding the cracks, potholes, and other stuff, and then displaying it on like a web page, which you can log into, or other forms. So it's very convenient for the user. So here you can see a short video where on the left upper side, you see the raw video, which was taken from the car. So you still see the hood in the video. Then in the lower left quadrant, we first detect where the road is. You see that here. And then in the right quadrant, it detects road anomalies, so cracks, potholes, and so on. And then depending on how much of these cracks there are, it will give an overall rating. So you see it just in a simple colors. And then this result then is displayed on a map. So here you can see each point is an image. You can click on those and see those images. And this is stuff is of course valuable for those who need to maintain the roads, make their pavement plans. So that's the things which we have done so far and successfully commercialized. Now we're working on the next generation. So this is ongoing research. And so with the previous one, we do those evaluations maybe once a year. But we want to do it more often. And in some cases, we want to do it even live. And so the idea is you put a system on a vehicle which drives around already, for example, a bus. It drives around all the time. And so every hour, along the same roads. Then you analyze the data and use it for infrastructure monitoring and other purposes. So what is different from the previous version is, so we want to have some live data. So some applications you want live. There's going to be so much data, so much video data from these vehicles. It's not possible to store them permanently. And there's only limited a bandwidth, cell, and even through Wi-Fi so you have to be selective of the data you want to store and further analyze. And we want to have multiple applications, not just one, but many different ones, and they might be very diverse. And you will see several, which I will introduce, which we're all working on right now. So, like 2 years ago, one student got the first shot at it, and so I call this second generation. What we call life map. So we wanted to show that it's possible to have the camera on the vehicle, take the data, analyze it on the vehicle itself, and then just send the important information. So you see it here schematically.
Christoph,
so you have,
I have a question.
Yeah, sure.
What is the important information that you are gathering data on?
So for, I mean, it is at the end user defined. For this particular experiment or a project, it was hazards, or which were in the form of traffic cones. So, I mean, that's user defined. Says, okay, I want to see wherever there's a new construction. We had it a lot around CMU. So I want to make everybody aware that there's somewhere construction. So I want to see where all the traffic cones are. So those are the hazards for this particular project, or for this particular experiment, which we used. But it, as I said, it can be user defined. We were also, it could be potholes, it could be dead animals, or anything else. So yeah, in general, user defined for this particular one, traffic cones. So we had our vehicle, and I mean, we used our Jeep for that, which has the video and the GPS. It analyzes the video, finds the hazards, in this case, the traffic cones. Then over a cellular phone, we send it to a database and have our own web server and can display it. You can always think about it as an automatic ways. You know, the Google Navigator ways where you can put it in, where the user can put it in by hand. This would do it automatically. And so here, so we were able to show the system running live, and so we recorded that live session, and I will play it for you in a second, just so you can see what all those different windows mean. So because it was live, we had a Skype session running at the same time, so that, well, so we can prove it it's live while we showed it to the people, but also that we can communicate and says, okay, now everybody's ready, so go ahead and drive. We are, you know. The second thing you will see is the raw camera feed. So this is the feed which we then analyze in the vehicle itself. Next, so here is the analyzed image. So you see that it detected all these traffic cones, and there's more of these traffic cones to come. So they will be, eventually we'll detect them. And whenever we detect the cones, we will can put it in a map. So each cone will get a symbol, and you can then click on it and see the image. So instead of then sending the full video stream, what we send are individual pictures whenever we found a new traffic cone. Okay, so and then here you see how it is going live. So here's the video. Here's, you see the car. It adds more and more of these cones. you can click on it and see those individual images. Okay, now here we just sped it up so that you don't have to wait till it comes here. Here comes the next cones here. So it sees some more. The user clicked on it, and here's you can see where they are in reality. So
I have another question, Christoph.
Sure.
What question or challenge were you setting out to address when you started this work?
The challenge, so we wanted to make use of the cars which are driving around already, make just add an inexpensive sensor like a camera, so that they can then record the surrounding of the vehicle, and then we can analyze that for many different applications. One, infrastructure monitoring, and many other things. There's so much information which we actually want from the environment, from, like how good are the roads, how bad is the traffic, that we think this will be a great way to look at the infrastructure, because otherwise you would have to send out a person to look at various different things which are broken in the environment or need to be fixed or so on. Okay. So what I just showed was the live version. We proof of principle of that we can do it live on a vehicle and have it back in a central location and look at it through a website, so that many people can then look at this at the same time. So the next generation is we want to put it on a bus. So this is then a step further on a wheeled system which can be employed, because buses already have cameras on them. They do that for security and liability reasons. The cameras are on there. If an accident happens, if something happens, if there's a claim against the bus driver or the bus company, they can pull out the video and say, okay, this is what happened, and this is the person who is liable, or so that's already on there. And it's not only the cameras which are all, on there. There's also the computer on there, which saves the video, stamps the GPS on it. So all the hardware is already there. So what we hope we have to do is that we have to add another application on the bus computer, which then can run this. Maybe add some more communication, cell connection or Wi-Fi connection. Now again, we will have limited bandwidth while the bus is driving on your cell, and then we might drive through places where there is no cell coverage. If we do need to download a little bit larger data sets, we might do that at the end of the day when the bus goes back to the garage and there's Wi-Fi, and then we can do some more over Wi-Fi. Then we also want to run multiple applications. So before you saw one application, now we want to do it with multiple applications. And we want to do that really on an hourly basis, or continuously while the car is driving. For each spot where it passes by would be then like once an hour. So that's a really dense amount of data. So here is sort of the system overview and with the applications. So you have the bus, which here in the center, with the cameras. And here are three applications which I'm going to talk about. One will be landslides, one will be traffic counts, and one will be updating HD maps. So you have the bus in collecting the data, analyzing them on there, but since there's only limited computation, it can only basically decide, is this interesting data or is this not interesting data? And if it's interesting data, then it can send it to a central location where it then might be analyzed more thoroughly, more accurately. Or like with the traffic count, it does the counting right on the bus and then just sends the number of counts. So that's much less information. Okay, so here, the first application you see here is traffic count. And you see here red and green rectangles. So the red ones are parked cars and the green ones are moving cars. And in the upper left corner, you see the total number of moving cars and the total number of parked cars. And both of them are interesting. So moving cars, I mean, you know, then if you ever used like a Google Navigator or similar application, it's very valuable to know what the traffic count is, what the current traffic is, so that you can plan better on maybe you take a detour or you travel at a different time. So we all experience that during rush hour. It's very good to know how bad the traffic is. So that's one thing, but of course for city planners, and they want to know what the traffic count is because they need to know if they need to change the design of the roads. Maintenance is different. If there's lots of traffic, maybe lots of trucks, then it destroys the road faster. Now with parked cars, it's a different thing. There's a whole thing. Well, if
Question,
you go,
Christoph?
sure.
How are the moving cars distinguished from the parked cars?
Yeah, that is actually tricky. So the short answer is we trained a deep network. Now, a deep network is always a little bit of a black box, so you don't know exactly what it does. But what we think it does, so we feed it two things. So one is the raw video, and we train and say, point out, so these are moving cars, these are parked cars. And just like we as humans can notice that a car is parked because it's very close to the curb, and then it's very close to the car in front or the car in the back. So that's one cue, but we also give it a motion cue because obviously the moving cars, they move around in the video, whereas the parked cars are fixed. So the technical term, it's what we use is optical flow images. So that basically says, you know, how much do things move in the image. We feed that also in the neural net. So, but simply speaking, it looks for visual cues, like it's close to the curb, and motion cues, like how fast is it moving in the image. And
okay,
yep.
I have another one. If it's counting the parked and moving cars, if the car is parked at a stoplight and the car is momentarily turned off, how would the counter know the difference?
I doesn't really know the difference. So we actually do tracking, meaning we have a video. So if we see one vehicle, we look at that vehicle for a while. So if it is in a spot where it's not moving and at first thinks it's parked, but then, you know, the light turns green and it starts moving, then we switch it to it's actually moving. So if a car is first classified parked and then classified as moving, then we can say, so, oh, it's actually a moving car. But I mean, at the end of the day, there will be always mistakes. And you can actually see here at this end of the movie, it does make a mistake that this car, it thinks it's a moving car. Maybe if we track it a little bit longer, it will notice that it's a parked car. You will always have some errors. Now you want to have, of course, a small number of errors. And when you look through the video, I think it does a very good job. And with the parked cars or moving cars, it's not so important that you have it very exact. I mean, if you're off by 5% or so, that's not usually not a big deal. So anyway, so thank you very much for those questions. I always like it if you ask questions.
I have one more.
Sure.
Is the classification of moving traffic compared to parked cars by lane location? Because in the video, there was a moving vehicle in the curb lane classified as a parked vehicle.
Because we're using deep networks, we actually don't really know what cues it uses. We think it uses any visual cue in the video. So where in the lane it is probably be a part of it. It's a little bit hand waving answer because it learned it, right? So we give it a lot of examples of moving cars, a lot of examples of parked cars, and we give it data input which we think has enough information in it, meaning like the video and the motion cues. What the deep learning then actually does, we don't really know. So it learns it by giving it a lot of examples. Okay.
Are there any future plans to expand this technology to other modes such as bicycles or pedestrians?
Oh, absolutely. Yeah. I mean, there's anything that people want to use. I mean, now it's going to be a work to do that. I don't know if in this mode that well, maybe pedestrian will be also good, but it's a little bit harder because they're on the sidewalk and they might be occluded by the parked cars. But yes, and actually bicycles is also very interesting because there's more and more bicyclists, and you really want to know all the new bicycle lanes which are being put in, for example, in Pittsburgh. You want to know, are they actually effective, right? I mean, there's discussion. People say, oh, we need them because you want to be bicycle friendly, and others says, hey, you're just taking away the lanes for the cars. And well, you can have this discussion about you really need data to say, well, if you put the lane in there, then it has these effects. It has, maybe there's more flow, maybe there's less flow. But without data, you can't have a good discussion about that. So yes, that would be certainly something we want to put in there at some point.
What were the key image pre-processing techniques used for the video analysis for these networks?
There was no pre-processing. I mean, it's really, you take example videos, label them and say, these are moving cars, these are parked cars, and then it learns it.
Okay, regarding post-processing of data, how is the information collected from a car, which is moving through traffic, mapped back to information about traffic along specific street segments, which are stationary?
Very good question. Very good question. So we of course have GPS. So this is actually the exact question you're asking is something which Ohio State University, which is a partner university of us, is addressing. So they say, I mean, actually they, part of their work inspired me also to do this, is exactly this translation from you're moving, the other are moving. What is the equivalent traffic count for if you would have the traditional method of either somebody standing at one place making notes or having these tubes and so on. And that is not trivial. And you actually do have to, for example, determine the speed of the moving cars to come up with that number. So it's a very good question, and it's addressed by somebody else, but by the partner of ours, and we're working with them together. So so that is certainly a problem. Okay. I see that's a very interesting feedback I'm getting here about the traffic count. So next application, landslides, and anybody who's here in Pittsburgh area knows a lot about it. And if you're driving on Route 30, when was it 2018, you had a big headache because for a couple months the road was closed. So this is certainly a big problem here, and this is also something we want to look at with the edge computing, with the bus on. Now this is pretty early in the research, and we not only have to train the detectors for that, but we even have to think about what are actually the interesting things to look at. And so things we have in mind right now is, for example, excess water or debris. I mean, if there's debris, then it has to come from somewhere, so somewhere else is washed out. Excess water might be a sign that the drainage is bad, and you need good drainage, because if the soil soaks up all that water, it becomes it reduces friction, and then it's when the landslide starts. And here on the right side, you see a road which is already broken, but you get certain when it starts, you get cracks which are here longitudinal, and then after a while it makes your curve, and then it's when it's really going to be bad. So these are things we want to look at, but we also need to have the data for that, right? So what are the actual indicators which says, oh, landslide is soon going to happen. Also, if you actually have a lot of pictures, you can make a 3D model of something. So you saw that. So on the right upper hand, you see one of the images. We took 80 of them all along that, and then we can make a 3D reconstruction like you saw below. Interesting things to look at is like walls which are starting to tilt, rail guards which are bent or falling down, and also trees. Actually, one thing I want to look at is if the soil moves a little bit, the trees might actually move a lot, so like a dial. So that is something I want to look at, and again, we need a lot of data for that, for a lot of time sequences of that. You know, one of the focuses we do right now is on development of cracks. Here you see an example, November 2018 and March 19, May 19, how this develops. This is also something we're working with civil engineering, so that if we have that data you just saw, like this development of those cracks and of that landslide within a time series, are they able to, or what are the appropriate models to model this kind of behavior? So here's like just a finite element analysis to see how a slope might have a landslide. So, and the third application, which I want to talk about is high definition map update. So for autonomous vehicles, and so this is Argo, that's because we are working with them on this project. So the situational awareness of autonomous vehicles is from its sensors, but also from a map. You need both. And the sensors then again update the map. So when you drive past, and then you can see did actually something change, and you can update it. But to get a good update, it's very expensive, because you would have to drive a vehicle like this with all the sensor and different laser scanners and so on. You have to do it continuously to keep it updated. So the idea which we have is, again, use the bus with the inexpensive sensors on them. And if they see some change, if you see some change, then you can update the high definition map. The big challenge is that the quality, especially the localization, meaning the GPS location of the data on the bus, is not very good. It's just the quality of a smartphone, so like 5 to 10 meters. Whereas the high definition maps, they are like centimeters or 10 centimeters in accuracy. So one challenge is the alignment. And then the second challenge is to detect if something has actually changed. And sometimes it might be just enough to say, oh, something changed. Because if you know that something changed, then somebody can go and look at it and say, oh yeah, there's something really changed and we need to update our HD maps. You could even send the expensive vehicle there if it's some larger update which needs to be made. But that already, this flagging that something needs to be looked at, that is already very valuable. The data which we work with, so we have the HD map, you see that on the left, like the roads with all the lanes very carefully annotated, plus images. Now these were taken at the same time, with the laser scanner, and they're very well located. So like within, centimeter, 10 centimeter. And then what we add from the bus is then camera data and the GPS, again, normal smartphone quality GPS. Now these example images I have here, they were actually taken with a smartphone. We don't have the bus yet equipped, and I hope that the current situation with the coronavirus goes over soon, so that we can do our tests there. What we do is we take first the images from the Argoverse, so from the well located images, and we do a 3D reconstruction with it. Same as I mentioned before, which I did for the landslide, for the 80 images, and then made a 3D model of the side of the road. So same way you can make here a 3D model. Now here it's very sparse. It's sparse because we could make that faster. But here you see these red things, these are all the various images, they're all aligned with each other. So suppose you have, these are the Argoverse images, we detect that there's a traffic sign, and then we align that with the map. So, the images are already aligned. We know where they are, and then you can find where the traffic sign is. And then when you have new images, so here these are the images which are taken in our case from the smartphone. You also see this image is actually taken from the left while the car was driving in the left lane. In the previous one, it was driving in the right lane. So here again are the images from the Argoverse, and with this 3D reconstruction, well, Colmap software, we can accurately align these images with these other images, and then can put these new images accurately inside the HD map. So here, these 3 points you see here correspond to these 3 images. And then these many points here to these many. Yep.
Question, Christoph?
Sure.
What is the next thing this technology might be used to detect? From the commercial side of the application, what are customers most interested in using the technology for?
I mean, there's the customers, they maybe sidewalks is an interesting thing, because there's not only that, yeah, you need to take care of the sidewalks, you also have to be ADA compliant. So a lot of sidewalks, they have problems because there's, you know, vegetation growing through them, or there's plates and they're offset, so you can't drive your wheelchair through that, or there's not enough space with it. So that is something we hear. We're also thinking about disaster. Like I mean, you can imagine if there's a hurricane going through an area, or a tornado, or a storm or something, that you want to analyze it very quickly and assess it. So you would send your vehicle through there, collect the data, and analyze that, so that you can see what the damage is. Now here in around Pittsburgh, the landslide is a big problem, and anything that can predict when a landslide is about to happen, or, you know, even if it's just like, oh, it looks dangerous right now, just close the road. That's already very useful, because it might, you know, save lives, it might save property. So these are things which I think are important.
Could there be
Go ahead.
Could there be a use case for this technology for enforcement, like if road openings or utility work was taking place without proper permits?
Sure. Yes. I'm a little bit wary for using it for enforcement, because this is going to be a lot of data, and we do have to have the trust of the people that were, you know, respecting their privacy. So I would prefer if one can separate those two, but in principle, yes, you can do the enforcement. What you might want to do is, you already have the enforcement using cameras for parking enforcement, right? You have those cameras on top of the vehicle. It reads the license plates, and if the license plates, and looks up if that vehicle has paid their dues and is allowed to park there. Now, that vehicle could also look for if you know, somebody is doing utility work when they're not supposed to. That is probably, well, just on a level of how to make all this acceptable to the population. It's probably better, because we know, okay, this car is there for enforcement. Police is there for enforcement. That's what they're going to do. I know, you know, but if you do it like in a, if you think that every bus which drives by is going to look at you and try to enforce something, that might be problematic in acceptance by the people. But from the technology side, yes, of course, this can be done. Okay, where were we here? Okay, so yeah, so in this case, now when we have new images, it can be aligned very nicely, and then we can see, you know, it detects traffic signs, can put it in the map, and then see if it is, if there already is a map in the HD map, so it already knows about it, or if it's new, or if it's not there anymore and has been removed or stolen or something. So yeah, that is, as I said, another project which we're doing. And what I also like about that project is sort of, it brings us back to autonomous driving, because autonomous driving needs those HD maps, and now we can again provide them. So here is again the system overview. It shows you all the applications we have. Thank you very much for your attention, and please go ahead and ask questions.
Okay, I have a question.
Sure.
How did you get interested in this research topic, and what got you started?
It got me started. It's this Traffic 21. So that was 10 years ago, a little bit more than 10 years ago. It's when Henry Hillman gave a donation to CMU and says, "Can you guys do something traffic research, which can be applied right now?" And I was in that research area of autonomous vehicles, and it's all very like at that time very far into the future. And I thought, what can I do right now? And then I came up with the idea of using smartphones to look at cracks in the road. Specifically, so the edge computing, it was, I was aware that if you want to scale the this crack detection, you can't send out your drivers. You have to put it on vehicles which drive around anyway, otherwise it's not scalable. But then you have to have then there's the problem that you have to deal with all the so many vehicles, and you have to monitor all their data collection and tell them what to do. And you can't all the problems I mentioned before. And I said, well, you need edge computing for that. So I then got together with Satya, it's a professor at CMU, who is doing that already for other things, and suggested this project. And then landslides, well, 2018 was a big year of big landslides, and I thought, well, maybe it's something I can do something about with the technology I have here. So that got me working on the landslide.
Okay, how much might this cost to implement, and what estimated costs might this save for the local government on the taxpayer?
Well, I hope that it actually, so to implement it on the bus, I hope that it will be very small, meaning the cameras are already in there, the computing is already in there. A lot of them already have communication. So it's almost like you're just adding another app on the bus itself, right? So the marginal cost might be small. Now, of course, you have to have the development cost and so on, and there's still maintenance and updates, but it should be fairly low. So, and we are already, talking with, the company which installs these systems, meaning the cameras and the computing on the buses, and those are, I think, like $10,000 or something like this. So if you would install it from scratch, it would maybe be $10,000, right? But a lot of them already have them on there, so it's just adding another application to that. So the amount people can save. So now, from the company I have, from the feedback we get is that they can, doing the inspection, with a camera instead of with a person, actually, somebody, yes, I just remember. Here it is. So just for the road inspection, we did a study where we, interviewed the, I think it was Savannah, the town. How much did they spend the previous year on inspection? So what they did is they sent people out, they make notes on the inspection, and it cost them like $250,000. The company did it with a smartphone for 50,000. So it's a factor of 5 cheaper, right? And the quality was better because you have not just notes, but you have actually pictures, and you have it all done in one shot and not in 3 years. So I think this is kind of like the dimension you can think of, the savings you have. I mean, if you need to do the inspection of landslides, I mean, you usually know which areas are prone to landslides, but it's very expensive to have to send someone like every year or even every month. And if you can do that automatically, yeah, you would save a lot. And the saving in life and property and traffic interruption, that might be huge. It's hard to quantify, but yeah, it might be very big.
Is there any way to incorporate multiple channels of information, for example, visual and vibration of roads and bridges? And in addition, what fidelity of data would be required to detect ahead of time something like the sinkhole in downtown Pittsburgh last year?
Oh, that's a good question. So yes, of course you can add the vibration data. I mean, actually, a smartphone does have an IMU, so a accelerometer and a gyro in there. You can add that to that and analyze it. Now, it's quite difficult to analyze that. I mean, people have done it. You can. I mean, there's tons and tons of papers written about it, but it's quite difficult because the vehicle itself is already vibrating, and then you have the you don't have direct contact onto the road, but you have the wheel, and you have the tire which damps it, and you have the shock absorber and so on. And it's really difficult to get very meaningful data out of that. But certainly it is there. Now with the sinkhole in downtown, it really depends on what were the signs which would have told you that it's happening. My rule of thumb is, if a person would be able to look at that area and then notice, oh, there's more cracks than usual, and there's, oh, these cracks, you know, they form a rectangle or something. If a person who would have been dedicated to looking at that, if he or she would have been able to detect it, then there's a good chance that camera images would also have been able to detect it. But I mean, if it was pristine and then the next second it fell through, there's nothing you can detect. If it's slowly moving and there's starting some cracks, possible that it's that it can be detected.
Okay, I want to thank everyone for their questions. We only have time for one more. With the recent announcement of the introduction of LiDAR to smartphones coming, could crowdsourcing of photos be on the horizon to help with predictions?
LiDAR on smartphones. Well, any data might be useful. I don't think that the LiDAR on smartphone will be very far-reaching. Just the amount of power you would need is, but sure. I mean, if you can mount the smartphone somewhere on the bus, somewhere on the vehicle, and it can actually reach the ground, maybe you point it directly down. Yes, then you could do that too. I mean, we already thinking about like what would be the next generation of this crowdsourcing from buses, and that might be you add sensors, you add like a air monitor, right? Then the bus is driving around and monitoring the air, or a gas monitor, methane gas, right? That can actually be dangerous. If there's somewhere a leak, you want to find it out as soon as possible. Yeah, so I mean, there's in principle nothing preventing of adding more sensors. It just might be a little bit more expensive.
Well, Joy, thank you for managing our questions and answers. And Christoph, thank you so much for sharing your work and giving the presentation today.
Can I just say one more thing?
Sure.
So, I mean, I have no idea who was all on the phone call or on the presentation, but feel free to email me if anything which I did here, it says, oh, we have this problem, you know, can you do that? Send me an email. I'm happy to discuss. I'm always happy to find new use cases and maybe places who want to try it out and so on. So don't hesitate to email me and keep this conversation going.
What a nice offer. Thank you. And I'd like to thank everyone for joining us today. As I mentioned at the beginning, the presentation will be posted on the Mobility21 website along with the link to the video, so you can access that later. For students who are interested in engaging in transportation topics, the Transportation Club on CMU campus is a great way to plug into transportation topics, and you get to meet all the other fellow transportation nerds on campus, which is cool. This afternoon, you will be receiving an email asking you to take a short survey about today's Smart Mobility Connection. Please take a few minutes to provide us feedback so we can continue to improve these sessions as we go forward. Next week, we will welcome Srinivas Narasimhan and Robert Tamburo as they talk about visual understanding of traffic at intersections, access to real-time information. You will need to register for that separately as the code to enter the meeting is different. Thanks again for attending today, and please feel free to contact me with any questions. Thanks, everyone.
Thank you.